Good morning, good afternoon, and good evening. I'm very happy to present my research work in the IEEE 11th International Symposium on Power Electronics for Distributed Generation Systems. The topic of my talk is the design and control optimization of a novel bypass embedded multi-level multi-cell inverter for HEV drives. The agenda of my talk will start from a survey of the current state of the art, the technological gaps, and the motivation of this work, followed by introduction with a novel bypass multi-level multi-cell inverter control design. MATLAB Simulink was used for verification of the control topology design to manipulate bidirectional current circulation in the regeneration braking. Multi-objective optimization was performed, targeting a balanced switching losses between switches, a minimum quantity of carriers, and a balanced state of charge between battery modules. Motor drives of hybrid electric vehicles (HEV) advance continuously with the development of cascaded H-bridge multi-level multi-cell inverters. Due to advantages over the conventional two-level inverters, such as reduced switching losses, lower rate of change in voltage, and less susceptible to electromagnetic interference. However, the MMI does exhibit three main drawbacks, such as the cost of large number of switching devices, complexity in driving circuit, and vulnerability of system failures due to the complexity. To be more specific for HEV drives, more and more stringent requirements in the fuel economy and fault tolerance challenge the current status of MMC in terms of control modules design. State-of-the-art fault tolerance bypass techniques reported so far are mainly for remediation purpose, but few study to our knowledge has concern with the manipulation of bidirectional current flow for the battery recharging during the regenerative braking. So this paper bridges the gap by tailoring the conventional phase deposition path width modulation with a novel bypass design for achieving both the fault tolerance and the battery recharging functionalities. As illustrated in the figure on the right, an 11-level MMI with 5 symmetric CHP modules, each with a 48 battery supply per phase to synthesize 240 volts phase to neutral voltage. Each of the brick modules is shown in the figure here. To synthesize the 240 volts phase to neutral voltage output in the staircase waveform, an output of 0 volts for each brick module is required for a certain time in each clock cycle. To achieve this, conventional methods are based on signals 1 and 2 simultaneously below, hence shutting off all the MOSFETs and blocking the current through the module, which however contradicts with the same current implication of all the CHP modules connected in series. To address this, we propose a novel solution by adding a bypass enable signal, see the blue block, for the upper MOSFET of each module. Control signals for each phase are constituted by the PD-PWM signals together with the bypass enable signals, as implemented in these figures using NOT gates. Level of the enable signal is decided by the modulation signal. Given either the signal 1 or 2 is in high level, the current circulated without problems, and therefore the enable signal is off. The enable signal kicks in and goes high when signals 1 and 2 are both in low levels. MOSFET 1 is turned on, allowing the positive current flow in short circuit through the body diode of MOSFET 2. Here we present the result by simulation. First, output voltage of each CHP module versus the time for phase A. They are superpositioned to synthesize the output phase to neutral voltages for each phase in the figure showing in the next slide. Yep, here it is. The targeted 240 volts phase to neutral voltage per phase is demonstrated in the shape of staircase to mimic the sinusoidal waveform. It is worth noting that During the regenerative braking, negative current recharging batteries, and the inverter control operation is analogous, which means that MOSFET 2 and the body diode of MOSFET 1 develop a path along which the negative current flows. In a summary, the proposed bypass arrangement enables the CHP MMI to manipulate the bidirectional current circulation, and therefore it is highly suitable for the motor drives and the regenerative braking in the HEV applications. In the first iteration of design, only the upper MOSFETs are in use for the bypass mode, resulting in higher switching losses and compromised lifespan as compared with the lower switches. A program selector for the loss equalization is proposed here, with the upper switches in use only for the first half cycle, and the lower switches put into operation for the second half cycle. Given all the H bridges share the same carrier frequency, the switching losses will be unequal among the bridges. As a sinusoidal reference intersects with the top and bottom carriers more frequently than the intermediate carriers, the switching losses increase accordingly from the center carrier to both sides. To balance the switching losses for longer service life and reduce maintenance costs, a hybrid carrier frequency scheme is proposed, with top and bottom carrier frequency 300 Hz smaller than that of the middle one at 600 Hz. As also illustrated in the figure here, the PD-PWM is further optimized by incorporating the carrier reduction to only 5 carriers per phase and reordering methods for balancing the state of charge between batteries, as well as the third harmonic injection for maximizing the DC supply utilization rate. Is the proposed hybrid control schemes optimized? The output line voltages of the inverter are presented, with multilevel waveforms approaching sinusoidal without filtering. Finally, the fast Fourier transform analysis was performed for the line voltage and the stator current, with the total harmonic distortions of 1.23% and 1.04% respectively, and the DC voltage utilization rate of 81.6%, all demonstrating a decent performance improvement and a reduced cost as compared with up-to-date documentations. The novel bypass embedded concept proposed in this work is not restricted for PD-PWM, but could also easily branch out into other PWM techniques and inform the future research directions and optimization. Thank you for your attention, and if you have any questions, feel free to email me. Thank you.